On August 20th, 2025, the James Webb Space Telescope pointed its infrared spectrograph at a small, ancient object racing through our solar system and returned a chemical reading so far outside anything astronomers had ever measured that the research team checked their own data multiple times before they believed it. The object was 3I Atlas, only the third interstellar comet ever confirmed to pass through our neighborhood, and the numbers coming back from Webb's instruments did not describe a comet that could have formed anywhere near our sun. This is the story of what Webb actually found buried in the light of a visitor that left its home star system before our own sun had even finished forming, why that chemistry forced scientists to rethink what protoplanetary disks around other stars can look like, and why the sprawling multi-observatory campaign built around this single object became the most comprehensive scientific engagement with an interstellar visitor in history. To understand why 3I Atlas mattered so much, you first need to understand how rare and recent this entire category of object actually is. For most of the history of astronomy, the idea of an interstellar object, a body that formed around another star and was later flung out into the galaxy, was pure theory. Astronomers had good statistical reasons to believe such objects should exist in enormous numbers, since planetary systems eject leftover material as they form, scattering comets and asteroids outward on trajectories fast enough to escape their parent star entirely. But theory is not observation, and for decades, nobody had actually caught one crossing our solar system. That changed in October 2017 when the Pan-STARRS telescope in Hawaii detected 1NI Oumuamua, a strange elongated object that showed no visible coma or tail despite repeated attempts to find one, and displayed a subtle, unexplained acceleration that fueled scientific debate for years afterward. Then, in 2019, astronomer Gennady Borisov discovered 2I Borisov, a genuinely active comet with a real tail, whose chemistry turned out to be broadly similar to comets born in our own solar system, differing mainly in an unusually high concentration of carbon monoxide. Neither of those first two visitors gave scientists much time or opportunity to study them in real depth. Oumuamua was already outbound and fading. By the time telescopes caught it, moving too fast for any spacecraft to intercept, and its strange shape elongated enough that some early models pictured something almost cigar-like tumbling through space, only deepened the mystery since a body with no visible coma should not have shown any measurable acceleration from anything other than gravity. Borisov, discovered 2 years later by an amateur astronomer using a telescope he built himself, behaved much more like a familiar comet, complete with an active tail, and detailed spectroscopy found its gas and dust genuinely comparable to solar system comets, differing mainly in an unusually strong enrichment of carbon monoxide relative to water. Between them, these two objects proved interstellar visitors were real and reachable with existing technology, but each one left scientists wanting more time, more data, and a genuinely detailed chemical fingerprint that neither object stuck around long enough to provide. Then, on July 1st, 2025, the Atlas Survey Telescope in Chile picked up a faint object later designated C2025N1, and within days, follow-up observations confirmed something remarkable: an eccentricity above 6, an inclination past 175 degrees, and a velocity relative to the Sun of roughly 58 kilometers per second. The unmistakable signature of an object on a hyperbolic trajectory that could never have originated inside our solar system. It was renamed 3I Atlas, the third confirmed interstellar interloper, and unlike its predecessors, it arrived at exactly the right time and angle for humanity's most powerful instruments to actually study it in depth before, during, and after its closest approach to the Sun in late October 2025. Before we get into exactly what Webb found, it helps to understand what a spectrograph is actually doing when it looks at a comet, because the technique itself is almost as interesting as the results. Every molecule absorbs and emits light at very specific wavelengths, a kind of fingerprint unique to its chemical structure. When sunlight warms a comet's surface and ices turn directly into gas, that gas glows and absorbs light in a pattern that a spectrograph can spread out and read, the same way a prism splits white light into a rainbow, except this rainbow contains dips and spikes that identify exactly which molecules are present and in what relative quantities. Think of it less like taking a photograph and more like running a barcode scanner across the comet's own light, translating a faint infrared glow into a precise inventory of water, carbon dioxide, carbon monoxide, and dozens of trace compounds hiding inside it. Webb's near-infrared spectrograph did precisely this to 3I Atlas, covering wavelengths from 0.6 to 5.3 micrometers, a range where the fingerprints of these key compounds are clearly visible in ways that ground-based telescopes simply cannot capture from underneath Earth's atmosphere, since water vapor and carbon dioxide in our own atmosphere would drown. out the faint signal from a comet hundreds of millions of kilometers away. If you're the kind of person who finds it fascinating that a machine can read the chemical composition of an object racing through space from hundreds of millions of kilometers away, go ahead and hit that like button right now, because the actual numbers Webb returned are where this story gets genuinely strange. Led by astrochemist Martin Cordner at NASA's Goddard Space Flight Center, the team found a coma, the cloud of gas and dust. Surrounding the comet's nucleus, dominated overwhelmingly by carbon dioxide rather than water, alongside detectable water vapor, carbon monoxide, water ice, dust, and a tentative signature of carbonyl sulfide. The critical number was the ratio between carbon dioxide and water in that coma, measured at 7.6, a figure roughly 18 times higher than the trend established by decades of observations of ordinary solar system comets at a similar distance from the Sun. Statistically, that result sat more than 4, standard deviations away from what researchers expected, a level of deviation that, in most fields of science, gets treated as a serious anomaly demanding an explanation, not a rounding error to shrug off. That single ratio carries real physical meaning, because different frozen compounds turn to gas at different temperatures, and therefore at different distances from a star, forming what astronomers call frost lines within a protoplanetary disk. Water ice, typically, sublimates much closer to a young star, while carbon dioxide remains frozen until you move much farther out into colder territory. A comet built primarily around carbon dioxide, actively releasing that gas at a distance from the Sun, where most solar system comets are still essentially dormant, points toward formation in an unusually cold, distant region of whatever disk it originally came from, or around a star, with a genuinely different chemical starting point than our own Sun ever had. Researchers also noted a second, possible explanation worth taking seriously, that the comet's outer layers may simply be less efficient at conducting the Sun's heat inward, suppressing water sublimation, relative to carbon dioxide, regardless of where the object actually formed. A reminder that even a striking chemical anomaly can have more than one plausible physical explanation, and that untangling the two required every subsequent observation the campaign would go on to gather. The second Webb campaign, conducted as the comet moved outward away from the Sun in December 2025 after its perihelion passage had warmed its ancient interior for the first time in billions of years, pushed the story even further. Researchers measured the ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen in the water detected in the coma, and found it roughly 30 times higher than typical solar system bodies. They measured methane relative to water and found a ratio around 11 times higher than any comet ever recorded in our own solar system. And they measured the ratio of carbon-13 to the far more common carbon-12, an isotopic signature that, combined with everything else, allowed the team to make a genuinely startling calculation about the comet's age. These results were published on June 22, 2026, in the journal Nature, and Cordner described the moment plainly, calling it a unique opportunity to study an ancient object from the distant galaxy that probably predates our Sun and solar system entirely. Working from the isotopic and chemical evidence, the research team estimated 3I Atlas formed somewhere between 10 and 12 billion years ago. Our own solar system, for comparison, is roughly 4.6 billion years old, meaning this comet had already been drifting through the galaxy, alone in the dark, for longer than our entire solar system has existed, before it ever crossed paths with our Sun. That age estimate lines up with an independent analysis built entirely differently, using orbital dynamics instead of chemistry. Researcher Matthew Hopkins at the University of Oxford had spent years building a predictive statistical model connecting an interstellar object's velocity to its likely age and galactic origin. Based on a well-established relationship in astronomy, older populations of stars tend to move faster relative to the Sun's local neighborhood, because billions of years of gravitational nudges from passing molecular clouds and spiral arms gradually scatter their velocities. When 3I Atlas was announced, Hopkins reportedly ran the discovery through his model almost immediately, and what came back was striking: a kinematic age estimate in the range of 3 to 11 billion years, with several analyses converging on roughly 7 billion years specifically, tracing its likely origin to the galaxy's thick disk, a structurally distinct, much older population of stars that sits above and below the thinner plane where our own Sun resides. The thick disk is populated overwhelmingly by stars formed more than 10 billion years ago, carrying a chemical composition that predates most of the heavy element enrichment produced by generations of stellar explosions since. Separate spectroscopic work measuring the comet's carbon and nitrogen isotope ratios reached the same conclusion independently, consistent with formation around an older, lower metallicity star, exactly the kind of star population that dominates the thick disk, A rare case of two completely different scientific methods, one based on orbital mechanics and one based on chemistry, arriving at the same remarkable answer without either team simply borrowing the other's conclusion. What makes 3I Atlas such a remarkable scientific opportunity is not just Webb's observations, but the sheer scale of the campaign that formed around it. Where Webb read the chemistry of the gas, the Hubble Space Telescope focused on the structure of the dust, capturing images beginning in July 2025 that revealed a distinct teardrop-shaped cocoon streaming off the sunward side of the nucleus, with background stars streaked into thin lines across the frame as Hubble tracked the comet's rapid, non-standard motion across the sky. David Jewett of UCLA, who led much of Hubble's imaging effort, used that data alongside careful surface brightness modeling to progressively narrow down the size of the nucleus itself, an exceptionally difficult measurement for any active comet, since the surrounding coma constantly obscures the solid body underneath it, essentially forcing researchers to mathematically subtract the glow of escaping gas and dust to guess at what remains hidden inside. Early estimates in August 2025 could only constrain the nucleus to somewhere between a few hundred meters and roughly 5.5 kilometers across, a frustratingly wide range for something astronomers were tracking in such detail. But a more refined analysis published in February 2026, using the comet's own brightness and an assumed reflectivity typical of cometary surfaces, pinned the effective radius down to approximately 1.3 kilometers, remarkably small for an object generating such a substantial chemically rich coma. Then, in late November 2025, something happened that had never happened before with any interstellar object. Japan's X-RISM satellite, alongside Europe's XMM Newton Observatory, turned toward 3I Atlas and detected genuine X-ray emissions surrounding the comet, a diffuse glow extending roughly 400,000 kilometers from the nucleus, farther than the distance separating the Earth from the Moon, produced by a process called charge exchange, where electrically charged particles in the solar wind collide with the comet's escaping gas and emit X-rays as a byproduct of that collision. Neither Oumuamua nor Borisov had ever produced a detectable X-ray signal despite genuine efforts to find one, which made this detection, gathered over roughly 17 hours of observation, a milestone entirely of its own. Confirmation that this comet's outgassing was genuinely extraordinary in scale, energetic enough to carve out an X-ray halo large enough to have swallowed every planet in the solar system placed side by side. If discoveries like this, an ancient wanderer from another star system getting the most thorough scientific examination of any interstellar visitor in history, are exactly the kind of story that keeps you coming back. Go ahead and subscribe now, because the data from this comet is still being processed. The spacecraft contributions didn't stop with Earth orbiting telescopes either. On November 6, 2025, NASA's Europa Clipper, currently cruising toward Jupiter's icy moon on an entirely unrelated mission, was redirected to spend several hours imaging 3I Atlas using its ultraviolet spectrograph from roughly 100 million miles away, detecting oxygen and hydrogen signatures consistent with active water ice sublimation, along with tails stretching millions of miles behind the nucleus. Around the same window, the European Space Agency's JWST spacecraft, en route to explore Jupiter's moons, turned its own instruments toward the comet as well, capturing views from a different angle that would take months to fully transmit back and analyze once JWST resumed use of its primary antenna. Together, these two spacecraft offered something no interstellar object had ever received before, near simultaneous observation from multiple independent vantage points scattered across the solar system. Perhaps the strangest twist in the entire 3I Atlas story only surfaced months after the fact. The newly operational Vera C. Rubin Observatory in Chile, still in its science validation phase and not yet officially conducting its full 10-year survey, happened to be scanning the very patch of sky where 3I Atlas was quietly moving, completely unnoticed, starting on June 21st, 2025, a full 10 days before the Atlas survey officially announced the discovery. Researchers led by Colin Orion Chandler at the University of Washington later combed back through Rubin's early commissioning images and recovered the comet sitting there in dozens of frames, some of the earliest and highest resolution images that exist of the object, captured entirely by accident before anyone on Earth even knew it was there. Out of 49 candidate images spanning June 21st through July 7th, 37 proved usable for analysis, showing the comet already developing a coma and, curiously, a faint tail pointed toward the sun rather than away from it, a rare geometric effect caused by larger dust grains lagging behind the nucleus along its orbital path. It is a genuinely remarkable footnote. A brand new billion-dollar observatory unknowingly photographing a visitor from another star system before the object even had a name, and a preview of exactly the kind of early detection Rubin is expected to provide routinely once its full survey begins. It's worth being clear about something before going further, because interstellar objects have a habit of attracting speculation that outruns the actual science. When Oumuamua showed its unexplained acceleration back in 2017, a small number of researchers, most prominently Harvard astronomer Avi Loeb, publicly raised the possibility of an artificial origin. And that same style of speculation resurfaced almost immediately around 3I Atlas, given its unusual chemistry, its considerable age, and its size. Loeb and a handful of collaborators published papers during 2025 arguing that some of the comet's properties, including its trajectory and the timing of its solar system passage, warranted closer scrutiny before ruling out an artificial explanation entirely. The overwhelming majority of researchers who actually gathered this data across every observatory involved in the campaign pushed back firmly on that framing, pointing out that every single measurement, the outgassing patterns, the dust morphology consistent with known cometary behavior, the isotopic ratios matching predictions for an ancient natural body, fits comfortably within the physics of ordinary cometary activity. Extraordinary claims require extraordinary evidence, and nothing gathered so far clears that bar. The scientific consensus, reflected in the peer-reviewed Nature paper itself, is that 3I Atlas behaves exactly like what it appears to be, an ancient natural comet with genuinely unusual but entirely explicable chemistry, not an artificial object of any kind. So what does 3I Atlas actually change about how scientists understand the universe? Before this comet, everything astronomers knew about how protoplanetary disks produce comets came from a sample size of exactly one, our own solar system. Every ratio, every frost line, every assumption about which volatile compounds should dominate a comet's chemistry was built entirely from objects that condensed out of the same disk that built Earth, Jupiter, and everything else orbiting our sun. 3I Atlas is the first genuinely detailed data point from somewhere else entirely. A comet built from ice that condensed around a different star, under different temperature conditions, at a point in the galaxy's history when the interstellar medium contained a different mix of elements than it does today. Roughly 10 billion years before stellar nucleosynthesis had enriched the galaxy with the heavier elements common in younger stars like our sun. That means the galaxy's comet-building chemistry is measurably more diverse than a single solar system could ever reveal on its own, and objects like 3I Atlas function almost like time capsules, carrying a chemical snapshot of conditions from an era of the galaxy that no living star has experienced, all the way to a telescope built specifically to read it. The research surrounding this single comet, spanning Webb, Hubble, X-RISM, Europa Clipper, JUICE, and the Vera Rubin Observatory, has already produced an enormous body of published science, with more papers analyzing the campaign's full dataset still being released well into 2026. Every one of the major chemical measurements, the elevated carbon dioxide, the excess methane, the enriched deuterium, the ancient isotopic fingerprint, points in the same direction, toward an object shaped by conditions this solar system never experienced. There is something worth sitting with in the fact that this level of detail was even possible at all. When Oumuamua passed through in 2017, Webb did not yet exist, and the tools available simply could not have produced anything close to the chemical portrait later captured of 3I Atlas. The gap between those two passages, less than a decade, represents one of the fastest jumps in observational capability in the history of planetary astronomy, and it means the next interstellar visitor, whatever astronomers eventually call it, will very likely be caught earlier and studied even more thoroughly than this one was, simply because the infrastructure built around chasing 3I Atlas will already be in place and ready. 3I Atlas is now departing our solar system permanently, following a hyperbolic path that guarantees it will never return, headed back out into the same interstellar darkness it spent 10 billion years crossing before it ever passed near a star that could warm it enough to reveal what it was made of. But the science built around its brief visit is far from finished. The Vera Rubin Observatory is now fully operational and scanning the entire southern sky every few nights, with a level of sensitivity that all but guarantees the next interstellar visitor will be caught earlier, tracked longer, and studied with instruments already calibrated by everything researchers learned chasing this one. For one narrow window in 2025 and 2026, a wanderer older than our own sun let humanity's most sophisticated telescopes read exactly what it was carrying, and the story of what that data still has left to reveal is only getting started. If this is the kind of story that makes you look up at the night sky a little differently, let me know in the comments what surprised you most, and stay subscribed, because whatever the next interstellar visitor turns out to be, this channel will be covering it the moment the data comes in.